We now discuss the work done by a variable force. Consider again the case of the work done by a constant force F acting on an object at an angle theta relative to its displacement s. In this case, the magnitude of the force and the angle theta are constant, and the work is equal to F cosine theta times s. Imagine, however, that the magnitude and the direction of the force change as the object is moved through a displacement s. One way to account for this changing force is to consider the F cosine theta versus s curve. We use F cosine theta rather than just F because it is the projection of the force in the direction of the displacement that matters when calculating the work. Let's examine the force versus displacement curve for drawing back the string of a compound bow. A compound bow uses a system of pulleys that is designed so that the required force rises to a maximum as the string is drawn back, but then falls to 60% of the maximum value when the string is fully drawn. This makes it easier to hold when fully drawn. The variable force through the full displacement of the string while drawing it back is represented by this force displacement graph. Just to note, the graph of a constant force is just a horizontal line, and if the force were constant, we could just calculate the work using W equals F cosine theta times s, but this is not the case here. In the case of a variable force, we can estimate the total work by breaking up the curve into tiny segments and then calculating the work as if the force were constant over each segment. For instance, if we take a small part of the force versus displacement curve for the compound bow, we divide up the displacement axis into tiny displacements delta S1, delta S2, etc. We then take the value of F cosine theta at the midpoint of each delta S segment and, assuming F cosine theta is constant over that small segment, calculate the work done in that segment. For instance, the work done, delta W1, in the first displacement segment, delta S1, is F cosine theta 1 times delta S1. As you can see, this is the area of the rectangle, not the area in square meters, but the length of one side of the rectangle, which is F cosine theta 1, which is in units of newtons, times the length of the other side, delta S1, which is in meters. The product is therefore Newton times meter, which is a joule, the unit of work. To estimate the total work under the curve, we can sum all of the contributions to the total work by adding the areas of each segment, or the work is approximately equal to F cosine theta 1 times delta S1 plus F cosine theta 2 times delta S2 plus F cosine theta 3 times delta S3, etc. The final result is that the total work done is equal to the total area beneath the force displacement graph. This is just an approximation, but it gets more and more accurate the finer we divide the graph, meaning the smaller we make the delta S segments, the more accurate it gets. The calculation becomes exact as delta S approaches 0. In the case of the compound bow, we only have to calculate the area under its F cosine theta versus S curve. This can be done a number of ways, for example, calculating the area of the columns as we had just done. In this case, however, we can count the number of squares. The amount of work represented by each square is W equals 9.00 newtons times 2.78 times 10 to the negative 2 meters, which equals 0.250 joules. The work is then W equals 242 squares approximately times 0.250 joules per square, which equals 60.5 joules. Notice that the number of squares, 242, is just an approximation because we had to estimate fractions of squares when doing the counting. In summary, the work done by a variable force of magnitude F in moving an object through a displacement of magnitude S is equal to the area under the graph of F cosine theta versus S. The angle theta is the angle between the force and the displacement.